Hi, everyone. Welcome to Next Big Future. I have my guest, Randy Kirk, who's going to prompt me when I get too deep into the weeds or to have clarification around my explanations about what's going on with the LK99 room temperature superconductor. So welcome, Randy.
I'm glad to be here. And yes, I have, I claim to be a college dropout in physics and chemistry because I loved them so much in high school. But somewhere along the line, I went, oh no, this is too much. And so, yes, I want to understand everything about this. And so I will interrupt you anytime I'm like, what?
Okay. So my explanation will be one, I'll get people up to speed about what the what's happening with LK99 superconductor, the Korean papers and development, and then I'll describe how tough the challenge is for this thing, why people have to be a bit patient upon it, and then I'm going to describe what I think is what the labs and the researchers should be doing to productionize the science of this thing in order to figure out how to get things working faster and improve things out. Okay, so starting off with, and then Randy can ask me questions, stepping as a layperson to get clarification about what I'm describing here. So LK99 stands for, I think, Lee and Kim, the two South Korean researchers who came up with the papers, but there's more people involved, 6 or 7 researchers at least in Korea. One of them got fired, and he rushed out his paper in order to get it out. But obviously they believe in it, otherwise, they wouldn't have pucked it out. But it is rushed. They didn't get everything they had. So superconductors are a huge deal because it's materials that can completely eliminate resistance and heat for applications. It's already an $8 billion a year industry in many things: MRI, levitating trains, maglev trains, fast computer chips. So there's many applications already there, but difficult because of the need to pay millions of dollars to get this thing super cold to do it. A little super cold or a lot super cold.
So when I was trying to explain this to my wife the other day, and we both came to the same conclusion, maybe we were right or wrong. The big deal with regard to moving electricity now, we think of it in terms of a copper wire, or we think of it in terms of our computer. The computer gets hot when we have it on our lap.
Yeah.
Our phone even gets hot.
Yeah.
Sometimes it gets too hot.
Yeah.
And then an electric wire gets hot. And then so you don't like that heat because that's resistance, which costs you in terms of having to either cool it down, or you have to have more copper in order to move the same amount of electricity. Am I getting something close?
Yeah. I think those are comparable things. So overall, our electrical grid, from power plants to transformers, like that, are moving all this energy around. Everything that we use, which is a huge amount, 18,000 to 20,000 terawatt hours per year for all electricity, that we lose half of what we generate, or even 2/3 of what we generate, depending on the situation, to heat, to transmission losses. And that's a big deal. But that's if you were able to make so much of this stuff that you could redo 1,000,000 miles of transmission line to make this stuff. So yes, that is an application. It's easy to understand one, but there are other smaller, like the cell phone type of thing that you're talking about, where we already have the difficult to use materials that superconduct that are able to go from 4 gigahertz computer chips to 800 gigahertz computer chips, where you make a little surface thing, and it does amazing things where you get like 200 times faster. And there's different economic value things, where basically, how valuable are the early applications where I use very little, and how much am I willing to pay for that, right?
Yeah.
I'm willing to pay $1 billion for a really good supercomputer. I'm willing to pay, many $billions for that, other really good applications where I could not do it any other way. The fact I could do it, but not as well, is nice. It can have a big, it's like getting, water or purified water. It's important, but I have to make so much of it, versus, a perfect diamond versus an imperfect diamond, right? A perfect diamond, it's the the sapphire of Africa or something like that, heart of Africa, versus this other thing. It's still diamond, but it's my $500 diamond versus 50 million. So a little can go a long way if it's freaking perfect.
Yeah. So
that's the difference with all these things of like, you have to think about where does it matter, where is it perfect when I have very little, because it's right now we're only making fan grain size pieces of this stuff.
Yeah.
Right. Which is something that people understand. I'm starting with a pound of material and I'm making a fan grain like thing of it. And it doesn't even work that well. So it's not even imperfect because I got to swap out, every eighth copper to get this thing. And I have to make it, the volume of this thing shrink by 0.48%.
Wait. What do you mean swap out? Okay. So you've got this grain of stuff.
Mm-hmm.
You have some atoms that are being swapped out. Is that swapped out when you get the grain, or after you get the grain, you still have to swap things out?
I'm making it with the swapping happening. So I'm basically taking lead phosphate, which kind of looks like a bone-like thing, and then I'm taking copper phosphorus, something like that, and then I'm pestling, like grinding stuff together, mixing it, and then baking it for like a day or something like that to make the stuff. So it's like this, very difficult baking process and mixing in the right ratio to do stuff, right? So it needs to be precise, but it's only statistically, kind of working out. And it's only 1 in a million times. I'm trying with a million times more, but only a millionth of it actually does kind of what I want it to do.
Works.
Kind of works, right? So it's like I'm starting with this, and 10% of the time, the entire batch is bad, right? 10% of the time, and it could be even more because one guy's trying to copy the recipe, and then he tries like 100 times and it screws up. Not because other guys can't do it 10% of the time if they get it right, but because he kind of like didn't get his steps right, didn't bake it right, didn't follow the magic souffle recipe, right? So it's difficult, even if you know what you're doing. The best that we know how is 10%, and then even if we know what you're doing, it's like a tiny flake, right? So really, really hard, right? And really unreliable at this point. But it's like I can pull Excalibur from the stone 1 in a billion times.
Yeah.
It's only 1 in a billion times. It's so hard. I pulled Excalibur from the stone. Get over yourself.
Yeah.
Right. So that's the thing, is that if you can pull Excalibur from the stone, I don't care how many times you had to try. Right. It's important because Excalibur from the stone. Right. So that's the thing. So then how do we go from here to there? One, you have to be patient. The researchers have to do their stuff, and they're trying, because we're talking about Excalibur from the stone, right? Where basically everything changes, where, we could have, one of the easier applications I thought of was a particular kind of space propulsion, where with a stronger, lighter magnet, we could go to Mars in a month, right? With a spacecraft, or where I just have like a fifth size amount of this stuff. Right.
So that would be as opposed to 3 months, something like that.
Yeah, opposed to 3 to 6 months or a year.
I see. Oh, I see. Okay.
Right. So I can go in a month, maybe like 2 weeks, something like that. It was just one simple thing that we've been making in an inferior way that we can make better. Right. And but the thing is, like, there's 1,000 different applications for things where if you can make things that much better, that much lighter, that much more powerful, right? Where you don't have to like make 1 million tons, 1 billion tons of stuff. I can make a very little, and I have something really super, like no other way to do it kind of thing, right? So there's multiple, unlimited, really kind of things once we go next level, right? It's like caveman with stone versus guy with copper tools, right? Versus guy with iron tools, right? It's like big leaps, right? You don't even know what the heck you're doing in between, right? Versus, so I'm going from stone tools to copper. I'm going go ahead.
So here's a question though that occurred to me the other day is like, okay, I'm only getting a grain out of every pound, let's say, or whatever. Let's say that it never gets any better than that.
Mm-hmm.
Would it still be worth it to keep putting in a pound and putting in a pound and getting out a grain?
So this goes to how I think they need to develop this thing, right?
Okay.
One, you want to be having a research thing to figure out how to up your reliability, right? I think there are ways there. One of the researchers who they dismiss as an amateur, but someone who worked as a soil scientist who's in Russia, made a batch in her kitchen and it performed particularly well. She thinks that maybe because she was using industrial phosphorus that had sulfur contamination, right? So it's like, we don't know which little pinch of whatever can do something to make this work a lot better, right? So if we get a pinch of this, a pinch of that, now we got, instead of a grain, I got a pea, right? So, but the thing is, if you can, I'd say that you don't know that after just 2 weeks of trying and only getting, less than 1% of the reports of what people are working on to say, I can make a conclusion about where this is going based upon this, very little information about what people can actually achieve with this stuff, right? And it still has to be proven out, right? So, work with graphene, took 4 years to go from 2 layers to 5 layers, and with a magic angle to make a superconductor out of that, right? So, unfortunately for people with internet attention spans, this will take time, right? But the thing is, the prize is so big, where basically our civilization goes up 1,000 times. I'm willing to give it a little bit of time to figure this out. But the thing is, so what do they do? They have to shorten up the cycle time. Can I get the 2-day bake cycle removed? Can I do a flash cooking thing? Can I make instead of just one batch at a time? Can I combinatorially try, 100 by 100 grid of different mixes where I adjust each one robotically to say I shift it from 4950, the ratio from 4950 to 151, and I have 100,000 at a batch. Boom, boom, boom. And
is this what's happening right now at Tesla's material science department?
So I would say you want to get there to that.
Is that what they're doing?
But you want to do smaller batches, 10 at a time, 100 at a time, something, and be able to test them. I need to have a proper verification, because making 100,000 doesn't mean no good if it still takes me a day to test each one to figure out if I did something, right? So they need to shorten up production. They need to speed up testing. They need to get reliability in testing. And so there's like a bunch of different knobs to turn on this thing before you say, okay, now I can reliably make 100,000. I can reliably test 100,000. I have a theory for it saying, which one should I be testing? Because I want the theory to say, okay, like China had a theory, they published a preprint saying silver and gold might work even better, right? So I want a theory, I need to validate the theory. So there's a bunch of theory testing that they need to do to improve what should I be looking at? What am I looking at? And then I need to get tools that are better at testing. And I need to up my throughput on this thing because,
So Berkeley Labs famously, they didn't go and put a test batch in the oven and cook it up to see what. They famously took the paper and said, okay, let's put this in the computer and let's see if this is real. Let's see if this is something that could work. Theoretically, they could, and again, I don't understand. It's kind of like, how do they fly? I don't know how that airplane gets off the ground. But still, would this also be true of what you're proposing? Is that if Tesla in their lab right now is making 1,000 batches a day and trying 1,000 different things, they would feed those 1,000 different results into a supercomputer, which would then use AI analysis to say, oh, well, based on what we're seeing now, try the next batch, try these 17 things. Is that
right? So it's a feedback loop between experiments feeding into a model, feeding into theory, feeding into a predictive model, feeding into the next experiment. So I'm using the data to improve my model. And I'm testing, am I correlating with what I say should be happening, right? Because if I'm not correlating, then my model is still no good, right? I need to be improved. I need to get that better to know that I'm predicting this. And so let's try that. Is that lined up? One, am I getting better results? Two, is it lined up with what I thought would happen? Right? And if it's not, I need to use the data to improve my predictive model and then try again, right?
Yeah.
And then you got to shorten up that cycle time. And that's the good thing about this thing being a room temperature with easy materials. Although sometimes they got to let's run it, cool it to see if things are different. Some of that testing needs to be done that way. But the fact that things might work at room temperature is different from, I made this test, I shoved it into a diamond anvil. It took me a week to get down to the diamond anvil pressure of 1 billion times current atmospheres, and I got to run special tools to do. The cycle time cannot get down more than a month, and the reliability can't get better than 5% or whatever like that, right? So that's the good thing about this one is we're already at room temperature, and you may want to do more at other temperatures, but a bulk of the work can happen where it is not theoretically impossible for them to ramp up this testing and stuff like that, and the feedback on the theory can happen so fast, right? Yeah. Whereas, and that's I think it's a new doorway, because the initial papers talked about making quantum wells, every whatever distance from it, right? Which is, and the fact that they could replace diamond anvils with a structural solid state changing of the structure, of what copper or whatever dopants are there. The fact that they could do that instead of this temperature pressure thing, right, means that the doorway to potentially new things is happening. So with superconducting at any temperature, yes, we want to be room temperature, but with superconducting at minus 100, it's still a new superconductor.
Right.
Being over 70 or 35 Kelvin, above absolute zero, is still exceptional in the world of superconductors.
Yeah.
And the fact that all we got to do is figure out what's going on, then maybe we can get that thing, that is still huge. So even though it may not be where the world changes with the first product in 2 years versus, we have this pathway to 1000x over 20 years.
Yeah.
It's still, hugely important to look at this. And, we need to wait some time. Mm-hmm. We will get better and better results. They're not going to keep a secret in terms of what they've developed for that long, right? Yeah. They want to be careful. They want to, dot their I's and cross their T's before they dump something, make some kind of reveal, they being the various national labs that are working on this thing, the fact that Tesla's or SpaceX are doing some stuff too, because it doesn't partial confirmation of something is not worthwhile for these people. They want to be able to say, here's how it fits in, here's the pathway to the promised land and to removing Excalibur from the stone. They want to say, I'm making a significant contribution analytically to tell the world that is happening, because that's a Nobel Prize. Nobel Prize for the Kim, if it proves out in any way to be true, and the other guys, and then another Nobel Prize for, I really figured this out in a better way and systematic, and we can now scale this up by 1,000. There's this thing has a dozen Nobel Prizes for each of the major steps, but I got to do a major step.
Yeah.
Me tossing in a kind of me too irrelevant. I got to give you something significant. I got to figure out something important about this thing, right? But they won't wait until it's perfect at the end to do it. There's like other things along the way,
Right.
Because there's been like 5 Nobel Prizes in superconducting already.
Wow.
Do we have room temperature superconductor already? No, we don't.
No,
right?
yeah.
But it's important enough that we already had 5, because like, oh, you got from like 5 degrees to 35 degrees, here, have a Nobel Prize.
Yeah, right.
Oh, you figured out how to go to 77 degrees, here, have a Nobel Prize. And 77 degrees is 77 Kelvin.
Yeah.
Not minus 270 up to minus 200.
Yeah.
Nobel Prize, right? So, okay, go ahead.
So one of the things that's being talked about a lot in this area has been the idea that you don't normally have somebody being able to replicate or to play or experiment with this in their kitchen,
right?
And so it's creating a very different atmosphere of what would you call it?
Citizen sciences, something.
Yeah.
Right, and social media science.
Yeah.
It's interesting, exciting right now. It will be that the most likely the big boy guys who can ramp it up by 1 million times and do 1 million different experiments at the same time, they have the advantage, right? Yeah. They'll do the stuff. The fact, though, that, if you can get a talented chemist, maybe this, I.S. Alexander, who tossed in a pinch of sulfur, maybe that was something, right? So there is some initial contributions on methodology and stuff, because this is still so new, right? Ultimately, it goes back to, I have a big lab. I've done stuff to make the production cycles go a lot more. I can test this thing at volume, and then we're going to roll it into big factories and stuff like that. It has to go that way, right?
Right. What's your feeling that Elon Musk has only uttered one phrase so far about superconductor?
Well, I told you before in one of our previous interviews on your channel that, for sure, this is one of those things where SpaceX and Tesla material engineers would investigate it. Will they keep doing it? It depends on how things play out.
Yeah.
Right. Because we have to figure this stuff out. But it is something where they would for sure try to look at it and maybe even keep a team trying to figure it out, because it's one of those things where, just like AI, being first, being on top of it is a huge advantage. Right. So not just taking stuff research, but occasionally doing their own experiments if they have an idea about it, because it's such a potentially wide open thing that they would want to stay on top of it, that and being able to apply it, to also be able to filter out BS, non-BS.
Yeah.
Right. Same thing for their batteries. They do the research to know. Some guys coming to me saying that they can do a 10 times better battery. It has to scale up in the factory. So they have to also know, can I scale this thing up? One thing on the car engine motor side of things, is that that the U.S. Navy spent millions of dollars on using those ceramic superconductors, which are very brittle. So you have to make tapes of it, you have to roll it. They use that to make an engine for not quite an aircraft carrier, but for a large ship, a 35 megawatt thing that weighed 1/3 the mass. So, but they had extra cooling, didn't care. The weight reduction was worth it, right? So they spent a decade with Grumman to make that thing, right? So that's using the inferior, difficult, brittle thing to make an engine that's 1/3 the weight, right? So all motors are like that. You could do that. But the thing is, again, you'd have to, would it be applicable for Model Y? Not if it costs $1 million per thing, right? So, can you get it so that it's really cheap? If you can, cheap scale mass production is worthwhile. But Tesla had some stuff where they had like 4 small magnetic batteries, and Sandy Monroe and his team took it apart. They stacked in a certain way where by stacking it, you doubled the magnetic field. They took some Hayback, whatever process that did that, right? So just 4 batteries, that kind of thing. So just 4 magnets do that kind of thing. So if I can increase the field with the coating, with the whatever, then that would be something that would, increase the power, the efficiency of the electrician. So that kind of like coating thing or whatever, improvement, other stuff like that. There's, they're working with electricity. This can make various electric magnet properties better. If I only need a little bit of it to have some kind of outside impact, it's worthwhile, right? So it's, they will keep their hand in it. And things like improving batteries, we're always working on improving the silicon anode, right? There's some reports that the Koreans in March said that, okay, we have a polymer that can increase the amount of silicon to, nearly 100% versus the 5% already in Tesla's anodes versus, 3 to 8% in other applications. There's 2,000 papers a month on how do I improve the silicon anode, right? Because if I improve silicon anode, I double the thing. I take $1 trillion thing, EV industry, and make it $2 trillion. So thousands of scientists on that. A far more minor miracle than what room temperature can do. But a miracle, worthwhile, worth thousands of researchers to do, right? So again, this is kind of like, this is a broadly applicable thing where the electronic properties, magnetic properties, fundamental, the miracle of electricity and magnets and going next level on this thing. Silicon anode, a tiny piece of the battery thing, potentially worth trillions of dollars. This thing, everything in electricity and magnetism, right? So that's why it's a huge deal. Any piece of this, any bit of the progress means a lot. And if you fully master it, that alone, fully mastering that, is a difference between us and something very near Star Trek. Right? In some ways better than Star Trek in many ways. It's just not the warp drive bit, right? But the other parts, the non, but still miraculous, the expanse level stuff, right?
Sure.
So that's the kind of thing that we're talking about when you get the full way, right? But steps along the way are huge, monetarily, scientifically, again, there's 100, 1,000 Nobel Prizes to be given away in each bit of the improvement here. So any other questions or
I think those are the main ones, Brian. I think I'm starting to feel like I have some sense of what's actually happening here.
But the thing is, still have to prove it. But I don't think we're gonna come up completely empty on this thing. I think that, there's too much interesting stuff here. I think there's a doorway. It's just like, how difficult is the doorway to get into? Is this opening it up? But we want to see some superconducting levels at any temperature. More stuff on the purity. There's stuff to be done there. But I think it's worth keeping a close eye on this thing for quite a while until if there's some definitive papers saying that this thing's going to work. But then there were definitive papers by guys on the AI side who said it would never work back in the 80s, right? Big important people said it would never work. And then it caused an AI winter before people said, no, here's a way to get ahead. So I think it's worth checking out. I'll keep you posted on it.
All right. Very cool.
Okay. Thanks for joining me, Randy.
Okay.
Everyone join us again on Next Big Future. Join Randy on his YouTube channel. What's your YouTube channel there?
Randy Kirk.
Randy Kirk. That's easy enough. And follow him on Patreon. Follow me at nextbigfuture.com. Follow me on Next Big Future on YouTube and on Twitter. So thanks everyone, and we'll keep you posted on this exciting development. World changing. We'll let you know when it happens and how long. Okay, thank you.